Hello, welcome to Maths with EJD. In this video, I'll be talking about geometric sequences. In the previous one, I had considered arithmetic sequences and everything associated with it. So here, our focus will be on geometric sequences, starting from the definition. How do we define geometric differences? Geometric sequences. And then we'll talk about the concept of common ratio, which is going to come up under the definition. And afterwards, we'll talk about the how to finding the nth term, finding the nth term, okay, finding the nth term. Next, we'll be talking about the sum of the first n terms of a geometric sequence. Then, um, afterwards, we'll be talking about sum to infinity, sum to infinity, sum to infinity. Then we can talk about infinite geometric series and convergence. So these are the things we'll be looking at as we go on with this. Of course, absolutely. We'll look at some applications, some real life applications. And finally, we'll look at examples relating to some of these real life applications too. Okay, so that's how it's going to be here. Now let's move on and talk about the definition. So we have the definition. Okay, now just like I said in the general introductory video to this series, so a geometric sequence is a sequence of numbers where each term is found by multiplying the previous term by a fixed non-zero a fixed non-zero number called the common ratio called the common ratio. Okay, so that's what a geometric sequence is. So next, let's talk about the common ratio itself now. Ratio. Common ratio. All right. So the common ratio, R, we use R for that. The common ratio R is the constant factor. It is the constant factor between consecutive terms, between consecutive terms of a geometric sequence. Okay. Uh, so we can say given a geometric sequence AN, which we can say is A1, comma A2, comma A3, comma A4, if you like, up to AN. So R can be given as A2 over A1 or A3 over A2. You can go on and on, A4 over A3, whatever, and it can go as far as AN over AN minus 1, or all the way to AN plus 1 over AN. So generally, right? So generally, R can be said to be AN plus 1 all over AN. Okay, that's how we find R. That's how we find R. So that's the idea of the common ratio. So we are going to apply all of this later, but let's move on to the next idea. So the next thing, okay, we've done definition, common ratio. Now let's talk about finding the nth term of a geometric sequence. Okay, finding the nth term, finding the nth term of a geometric sequence. So finding the nth term. Now imagine, uh, let me say, given 2, 6, 18. Okay, given 2, 6, 18, and so on, right? Of course, this implies that the first term, A1, is equal to 2, and the common difference is 6 over 2 or 18 over 6, which is 3, given that's established, right? So that's all we have there. So now let's see how we can find the nth term from this concept. Now, you see here that if we go the first term A1 is 2, the second term A2 is 6, the third term is 18. Of course, the fourth term will be 18 times 3, which is 54. The fifth term will be 54 times 3, which is 162, I believe. 5 times 4, 3 times 4 is 12, hold 1. 3 times 5, 15. So that 162. So we have all of this. And from what you see here, right, this can actually be written as 2, and this is 2 times 3. Next, you have 2 times 3 times 3. Next, you have 2 times 3 times 3 times 3 again, and then you have 2 times 3 in 4 places. Okay? All right. So that means that this is actually something like 2 times 3 raised to power 1. This is 2 times 3 raised to power 2. Okay, sorry, some perfectionism coming in here. Let me try to alternate the markers to make the points clearer. So this is like 2 times 3 raised to power 1. This is 2 times 3 raised to power 2. This is 2 times 3 raised to power 3. And this is 2 times 3, 2 times 3 raised to power 4. Now, can you see a pattern? This is so this can just be 2 times 3 raised to power 0. Now, if you look properly, you discover that the power on top of the common ratio is actually 1 less than the number of terms. So if the number is 1, we have 3 raised to power 0. If it is 2, it's 3, 1, 3 raised to power 0, 2, 3 raised to power 1, 3, 3 raised to power 2, 4, 3 raised to power 3, 5, 3 raised to power 4. So it looks like we have a pattern being established already that we can hold on to, and that is the fact that this is like 2 times 3 raised to power 1 minus 1. This is 2 times 3 raised to power 2 minus 1. This is 2 times 3 raised to power 3 minus 1. This is 2 times 3 raised to power 3 raised to power 4 minus 1. Okay, 4 minus 1. And this is 2 times 3 raised to power 5 minus 1. So if we extend this to n, okay, if we extend it to n and we are looking for an now, so that will look like we have generally the first term a1, the common ratio r, and the common ratio r, right? And the number of terms n. So so that means that an is something like a1 times r raised to power n minus 1. All right. So we can emphasize that in all, the nth term an is actually a1 r raised to power n minus 1. And this becomes the formula with which you can obtain the nth term of a geometric sequence. Okay, so now this is we have found the n term. So the next thing we are going to do is to find the sum of the first n terms. That's the next thing. Sum of the first n terms. Sum sum of the first n terms. Okay, just like what we did with the arithmetic progression. So we want to find the sum of the first n terms. Now imagine that you have the sequence an, okay, which is represented this way as a1, a2, a3, all the way down to an. Now we want to find Sn. Sn is more like its series because the series is the sum of a sequence, sum of the terms of a sequence. So you have, imagine we now need Sn, which is A1 plus A2 plus A3 plus let me go to A4 this time, plus all that down to AN. Okay. And we already know what these expressions are because we know that okay, I let me play with the colors I have. So I have SN now to be A1. A2 now we know that is A1 raised power R. You know, we keep multiplying the first term by R and as we progress. So the next term, so this is A raised power A1R. This will be A1R times R. That's A1R squared plus this is now A1 R raised power 3, like we know already, plus all that down to A1 R raised power N here. So that's N minus 1. So we have that expression that is for Sn. Now, what we're going to do next is to multiply, multiply Sn by the common ratio R. So what does that give us? So that tells us that we now have Rsn equals A1R plus A1 R squared. You know, we're multiplying each term by R. So the third term will now be A1 R cubed. Then the fourth term will be A1 R4 plus all that. So the last term will now be AR. The last term will be A1 R raised to power N, you know, because we have leveled things up. Okay. So the next thing we want to do now is to, you know, want to derive how to sum up things here. So we now multiply, we now subtract. So we subtract RSN from SN. So what that simply means now is that we now have, okay, it's important to see what's happening here. So we now have Sn minus Rsn. And that is simply, now let's see what's happening here. So Sn minus Rsn. So if you look at the terms, you see this can easily knock this out, okay? So, you know, we are saying all this minus all this, right? So this can knock this out. This will knock this out. This will knock this out. Now, of course, if you continue to AR4 will knock something out here. Then this ARN minus 1, before A1R here, we also have A1RN minus 1. So this will surely knock that out. So what do we have? We finally end up having this A1 here, minus A1 Rn. Okay, we have that. So if that is the case, we can also factorize this side. So we have Sn into 1 minus R equals A1 is common into 1 minus R raised to power N. So we can divide through by 1 minus R. So we have Sn equals A1 into 1 minus R raised to power N all over 1 minus R. And that becomes the beautiful formula that we need to compute the sum to the sum of the first n terms of a GP, okay, of a geometric progression or a geometric series. But it is important that R should not be equal to 1. That's extremely important because if R is equal to 1, the function, because of this part, it will be on the function will be undefined, okay? So don't forget here that the terms are like this. This is first term. Okay, this is the first term. So this is the sum to the nth term, if you like, sum to the nth term. So this is common ratio. The R is the common ratio. Then we have n, that's number of terms, whatever number of terms you're considering, number of terms. Okay. Then what else? Yeah, that's basically it. So that is the formula. For emphasis, I rewrite, I say, so the sum of the first n terms, or the sum to the nth term, like I like to call it, the sum of the first n terms of a geometric sequence, of a geometric sequence is found using this formula. Sn equals A1 into 1 minus R raised to power N all over 1 minus R. Really important formula right there. Of course, given that R is not equal to 1. Really important to note that. Okay, so that is the sum. I think I like to do everything before I take an example so that the example can be all encompassing. So we have done that. Now, let me see. The next thing I like to talk about is the sum to infinity. Sum to infinity. Okay, talking about the sum to infinity, right? Let's go for that. Sum to infinity. So have sum to infinity for a geometric series. Again, imagine that uh you have the geometric series, the geometric sequence, this A1, A2, A3 down to AN, okay? And then of course we already know that the sum is something like this. Sum is A1, okay, plus A1R plus A1R squared plus all that down to AR n minus 1. Okay, so the sum to infinity, the sum, okay, I guess I want to go, the sum to infinity is given as Sn, S infinity now. So S infinity, which is equal to the first term A1 divided by 1 minus the common ratio. Okay. So, okay. Now we have this to be sum to infinity. Okay. Of course, again, this is first term and R here is common ratio. That's how to find the sum to infinity for a geometric sequence. Okay. Now, um, okay, now we are done with sum to infinity. So we now want to talk about infinite geometric series and convergence. Infinite geometric series and convergence. So infinite geometric series and convergence. That's closely related with what we just did. Okay. So an infinite geometric series. Okay, that's just what we did up there, right? So an infinite geometric series, an infinite geometric series is the sum of the terms, the sum of the terms of a geometric sequence, some of the terms of a geometric sequence that continues indefinitely, that continues indefinitely, that continues indefinitely. Okay. Um, so the sum of an infinite geometric series, the sum of an infinite geometric series actually converges. It converges. That means that it has a finite sum, has a finite sum if the absolute value, if the absolute value of the common ratio, if the of the common absolute value of the common ratio is less than 1. Okay. So by the implication, we are saying that absolute value of the common ratio is less than 1. So, and just like we saw before, the sum, the sum is given by S infinity, which is equal to first term over 1 minus R, first term over 1, first term over 1 minus R for absolute value of R less than 1, just like we saw up there now. Okay. So that is the sum. That's the sum of that. Okay, I'm saving all the examples at the end so that we just take an example that encompasses so many things. That encompasses everything we would have learned in the process. So we've talked about that. So let's go for applications now. And then after applications, take examples. So applications. So what are some applications of geometric sequence? So applications, applications of geometric sequence. All right. So we have that. Okay, I mean, there's no point writing all these stories. Geometric sequences have many practical applications, right? We have it in population growth. Okay. So if a population grows by a fixed percentage each year, the size of the population follows a geometric sequence. Okay. We also have it in financial calculations. Financial calculations. In fact, we're going to take an example on compound interest. So we have financial calculations. Okay. So compound interest is based on geometric sequence. So I think that is worth mentioning. Compound interest. Compound interest, or even depreciation. Okay. Something can depreciate geometrically. Depreciation is also possible here. Then we have it in physics and engineering. So you have physics, and engineering. Physics and engineering. So geometric sequences model certain phenomena such as the decay of radioactive substances. Now it's really very popular for decay. So radioactive decay, like it is called radioactive decay, all right? Uh, or the vibration of mechanical systems. So we can talk about vibrations too. Uh, so of course, up here we can talk about population increase or decrease, right? I mean, it's a concern in many countries right now that populations are declining sharply. So, yeah, so those are some applications of geometric sequence. So to round off everything, let's take two examples to drive all these points home. So let's go for example one. Example one. So I'll use uh the GP we've been the geometric series we've been working with. Given 2, 6, 18, and so on. Okay. Find the one, the, let's say something simple, fifth term. Okay. Let's find the fifth term. Two, sum of the first five terms, or I can say sum to the fifth term, sum of the first five terms. Three, that's going to be your own to try. So we also want to find the, say, 11th term. Okay, let's find the 11th term. And four, finally, for this, find the sum of the first 11 terms. So I'm going to do just one and two, then you can try your hands on this. See, practice this, practice. Or let me just say try, try. Okay, so let's go for the solution now. Solution. Again, we have 2, 6, 18. All right. 2, 6, 18, and so on. And first question tells us to look for A5. A5 is what we need. Of course, we know from the geometric sequence, right? A1 is equal to 2. Then common ratio is 6 over 2, or if you like, 18 over 6, like we did before, which is 3. So now our n here is 5. And we know that an is given as a1 r raised to power n minus 1. Okay. So that means that we can then say a5 is equal to a1. A1 is 2 times common ratio, that's 3, raised to power 5 minus 1. Okay. So a5 is equal to 2 times 3 raised to power 4. 5 minus 1 is 4. So a5 is equal to 2 times 81. And 2 times 81, is 162. So that is what A5 should be. And of course, we can easily check that out. We know that we have 2 times 3, 6. 6 times 3, 18. 18 times 3, 54. 54 times 3 is 162. So this is 1, 2, 3, 4, 5. So this is actually A5. We can check that. All right. So we also need to find sum to the fifth term, right? We want to find sum of the first 5 terms. So 2 now, you need S5, okay? We need S5. And to find S5, of course, the formula to use is Sn, which is A1 into 1 minus R raised to power n divided by 1 minus R, given that R is not equal to 1, okay? To make sure the expression is always defined. In fact, R equals 1 is not going to make sense even because the values will remain constant, okay? So here we have A1 equals, again, we have A1 to be 2, common ratio is 3, then N is equal to 5. So we can just plug all of that in, and then we get what we need to get. So we have now that S5 is equal to 2 into 1 minus R, that is 3 raised to power 5, all over 1 minus R, which is 3, okay? So we have to battle with this. So this is 2 into 1 minus 3 raised to power 5. 3 raised to power 4 is 81. 81 times 5 is 405, I believe, divided by 1 minus 3, that's minus 2. Okay, so we have S5 equals 2 into minus 404 divided by minus 2. So 2 cancels 2, this cancels this. So S5 is 404. So sum of the first 5 terms is 404. Can we check that out? So we have 2, we have 6, we have 18, we have 54, and we have 162. So 2 plus 6 is 8. 8 plus 18 is 26. 26 plus 54 is 26 plus 54. Yeah, 26. This is 8. 26 plus 54 should be 80. Then 80 plus 162. I guess something is not right. Yeah. 54, 26, 18. Sum to the fifth term, right? 162. So okay, let's see what's actually wrong here. A1 is 2, R is 3. Okay. What's the formula we obtained again? It's 1 minus R, 1 minus R. Yeah, I think we're good. So what is wrong here? 3 raised to power 5. 3, 3 raised to power 4 is 81. 81 times 3. Ah, okay, that's my fault. Yeah, I did something quite not right. Okay, so that's not correct. So yeah, so my math is not mathing. So thankfully it's very easy to check. Uh okay. So I think I just jumped. Now 3 raised to power 4 is 81. 81 times 3 is now 3 243, right? Yeah, 243. Correct. 243. 243. Yes. So this is 243. Okay, so this is 2 into 1 minus 242, because 1 minus 243 is minus 242 divided by minus 2. So 2 cancels 2, and minus cancels minus. So S5 is not 404, it's actually 242. So we have 242. So it's good to always be able to check. So you have 2, 6, 18, 54, 162. Like I was saying, this is 8. This is 8 plus 18, 26. 26 plus 54 is 70. I mean, that's 80. Yeah. 80 plus 162. So 162, 80. This is 2. This is 4. And this is 2. So everything is 242. So checked. So this is good. Now, one thing I did not ask you to find is sum to infinity. So let me just say that's number 5. Find the sum to infinity, or find the infinite sum, so to speak. So to find the sum to infinity, which is number 5. So I mean, your job is to do number 3. So number 3, number 4, you do all that. So now number 5, to find sum to infinity, S infinity. So we know that S infinity is A1 over 1 minus R, okay? And we know that A1 is equal to 2 in our case, R is 3, and that's all we need for this. So S infinity now is first term, which is 2. That's 2 divided by 1 minus 3, okay? So the sum to infinity now is equal to 2 over minus 2. So sum to infinity is equal to minus 1 in this case. And that goes. All right. And that's about example 1. So don't forget your part of the task, questions 3 and 4. So let me take example 2, which will be a practical example about compound interest, because that's one very good area of application. So example 2, okay. Example 2 now, talking about compound interest. Compound interest. Okay. So if you invest $1,000 at an interest rate, at an interest rate of 5% compounded annually, the balance after n years follows a geometric sequence. So it follows a geometric sequence. Okay. So we can say that the end term is given by an. Of course, we know generally an is a1 into, okay, let me just follow what we have. So the end term is given by an equals the first term, which is the 1,000 you invested, multiplied by 1 plus the uh the percentage increase, which is 5 over 100 raised to power the number of years raised to power n. Okay, so that's more like so if n is equal to 3 years, right? If the investment goes on for 3 years, so what is the amount you are going to have be at the end of 3 years? So in that case, now we have A3. So that'll be A3 equals 1,000 into 1 plus 5 over 100, 5%, 5 over 100 raised to power 3. So A3 is equal to 1,000 into 1 plus 5 over 100 is 0.05 raised power 3. So that we have A3 equals 1,000. Okay, 1,000 times 1,000 times, say 1,000 times 1.05 raised power 3. And what is 1.05 raised power 3? So let me be very sure of that. 1.05 raised power 3. Okay. 1.05 multiplied by itself 3 times. Okay. So 1.05 raised to power 3 raised to power 3. That is 1.1576, all that. Okay. So that means that A3, so A3 would be 1,000 times 1.157625, so that we have A3 to be equal to 1157.63. So the investments would have matured to, so we can say, therefore, so after 3 years, After 3 years, the balance, the balance, the balance is uh $1,157.63. Okay. So in conclusion, right? In conclusion, so we can see that geometric sequences, geometric sequences model situations, the model situations where growth or decay happens at a constant rate, at a constant rate, making them, making them an essential tool, making them an essential tool in many fields. Okay. All right, so that's it for this video on geometric sequences, where we have considered all the necessary parts. So you don't forget to try the question out that I gave you. And of course, because after now we're talking about recursive sequences, so you want to subscribe to the channel and hit the notification bell so you can always get alerted each time a new video is released. Also comment, let me know how helpful these videos are, and also let me know if you want me to solve a problem or teach it on a particular topic, and then like and share so that more people can have access to this great content going on here. Till I come your way again, have a nice time. Bye.